Good evening, everyone. My name is Andrew Fracknoy. I'm the Emeritus Chair of the Astronomy Department at Foothill College, and I'd like to welcome all of you here at the Smithwick Theater at Foothill College in Los Altos Hills, and all of you watching on YouTube or listening on podcasts to this lecture in the 25th anniversary year of the Silicon Valley Astronomy Lectures. These programs are jointly sponsored by the Foothill College Science, Technology, Engineering, and Math Division in Los Altos Hills, by the Astronomical Society of the Pacific, an organization devoted to sharing astronomy with the public, and with the SETI Institute, the Search for Extraterrestrial Intelligence Institute, which is devoted to the science and education of finding life in the universe. And we appreciate all their help in getting the word out about the series. If you are watching us on YouTube for the first time, we encourage you to like and subscribe to our channel. And if you hit the notification bell, you will then be notified as new lectures come on board. And you can also, of course, enjoy all the back lectures going back more than 2 decades. Let me introduce tonight's talk. We're very fortunate to have with us Dr. Darlene Lim. Dr. Lim is a research scientist at the NASA Ames Research Center in Mountain View. She's conducted field research around the world on land and underwater, and has served as the principal investigator of several research programs investigating both Earth and space. She is the deputy principal investigator for the FINESS program and a co-investigator on numerous other NASA research and analog programs. She was the co-chair from 2009 to 2016 of a key group analyzing our country's Mars exploration program goals, and is a member of the National Oceanic and Atmospheric Administration Ocean Exploration Advisory Board from 2014 to 2021. So Dr. Lim is an expert in both science and organization, and tonight she's going to talk about real-time collaborative science operations at the South Pole of the Moon and beyond. Ladies and gentlemen, it's a privilege to present to you Dr. Darlene Lim.
So much, thank you. Hello, everybody. First, I want to say thank you so much to the Foothill College for allowing me to be here this evening, to the Silicon Valley Astronomy Series, and Jeff and Andrew, thank you so much for reaching out, for giving me this opportunity to come here tonight. And most of all, I really appreciate that everybody made the trek, came up the hill to spend the evening together this evening. And I'm really looking forward to seeing what your reactions are to the work. So I'm just going to back up. Looks like a button got pushed, and so you're actually getting the punchline a little bit, so we'll go back to the beginning. So as Andrew mentioned, I'm going to talk to you about some work that I've been doing since coming to NASA over the last 20 years. It's been research-based, but then it's made its way into the applied realm as we've applied the knowledge, the lessons that we've learned through the research that I'll share with you towards a flight mission that's headed to the lunar South Pole. And as you know, NASA is making a huge push to go back to the moon and then onwards to Mars, but not to the familiar landscapes of the Apollo era, where we managed to send, 6 different missions that had humans on board to the surface of the moon, as shown by those markers there. Instead, we have a different journey ahead of us. Many missions, starting as soon as next month, you're going to start seeing will head to the lunar South Pole, and specifically to an area called the Nobile region. This is a very interesting area, and you'll see a lot of missions that NASA has in the pipeline actually going there to look for resources to sustain humanity as we start to make our next kind of adventure happen towards sustaining a human presence on the moon and then elsewhere in the solar system in places such as Mars. So I have been actually working on a different mission, or one of the missions that was to head to the moon actually last fall. It's called the Viper mission, and some of you may have seen in the news that we were canceled. We're actually in a period of transition, and so I want to share with you a little bit about this mission and tell you that we're still, there's still a possibility that something may actually progress and you may actually see this mission come to actual fruition and make its way onto the moon. That's to be determined. That's part of our adventure. So this mission is really interesting in that, as I mentioned, it's headed to the lunar South Pole. It was to take place over 100 days, and it was to traverse 15 kilometers across the lunar South Pole. And it would be a traverse that would take us from sunlit regions all the way into areas called permanently shadowed regions. These are areas which have been in the permanent shadow for probably about 2 billion years at a time, and they're completely in the dark in most areas. So this is a very exciting mission, and one of the things that made it particularly interesting is the operational kind of paradigm that we were dealing with. So this is a model of actually what the shadows look like as they move across the lunar landscape. This is a very hilly lunar landscape in the lunar South Pole, and that red arrow is actually showing the rover kind of moving across a traverse that we modeled for the Viper mission. And you'll see that the shadows are kind of ebbing and they're flowing. And effectively, this rover, which is a solar-powered rover, is staying in this animation just slightly ahead of the, let's actually try it again so you can see it one more time, slightly ahead of the shadows. So the top speed of this rover is about 1 centimeter per second, which is akin to the top speed of like a giant tortoise. So I know that's not too exciting, but it's about 15 times as fast as some of the Mars rovers we've had, such as Curiosity. So it's pretty fast. And as I mentioned, it's a solar-powered rover. So the speed, while it may not be overwhelming to you after just having been down 280, it actually is quite important to note that it is fast for a rover, and it also is important that we note that it's just fast enough to stay ahead of those shadows as they ebb and they flow. I don't know if any of you have actually lived in the north or been to northern Canada in the wintertime. I actually grew up in Alberta in Canada. When I would walk home at the end of the day from school, the shadows were very low and very long, and they were kind of eerie. And so this is very much what I imagine the rover will experience when it actually is traversing across the lunar landscape. Now, mind you, I could run home. I wasn't, kind of reliant on the sun as our friend is here. And that actually is a really important matter when it comes to how we operate this rover. So the sustained speed that I talked about, which is about 1 centimeter per second, this is only possible when we actually have a line of sight that is actually, between the Earth and the moon itself, line of sight antenna signaling that is connected between those two planets. And that's because we actually teleoperate the rover from right here in the San Francisco Bay Area, from NASA Ames, which is just up the street from us here. It's probably like a 10-minute drive. Now, what's interesting is that because we're at the lunar South Pole and the way that the moon and the Earth are oriented, we will actually see this kind of ebb and flow in the horizon from the rover's vantage point of the Earth itself, which means that anytime that the Earth is dropping below that horizon line, we don't actually have that line of sight connection. That happens about every 2 weeks. So for 2 weeks, we have connectivity. We can teleoperate the rover 24/7, 24 hours a day, 7 days a week. But then for 2 weeks of a month, we actually go into a period where we lose that line of sight and the rover is completely cut off. That's called a safe haven period. So the rover would actually go into a hibernation mode, and it would have to endure, in some cases, about 50 hours of complete darkness. And we don't actually have, again, we don't have any communication with the rover over that time. But then as the Earth rises, it all starts over again. So we kind of go 2 weeks on, 2 weeks off. It's kind of the most wackadoodle shift work ever. But it goes on for months at a time, which for a science team, for an operations team, it will be extremely grueling. So this is something we spent hundreds of hours preparing for with our team, because again, we're running the operation 24/7. Now, the whole reason that we would put ourselves as humans through this, and of course this rover, and I want to mention that as the rover, ebbs and flows itself from the sunlit areas to the dark areas, the permanently shadowed regions, it will experience a temperature change anywhere from 30 Kelvin, so about minus 230 Celsius, all the way, up into the like 30 degrees Celsius kind of realm when it actually hits the sunlit areas. So those are incredible temperature swings. Again, the operational conditions are pretty rough as well, both for the humans that are involved with the mission as well as the rover itself. And so the reason we go through all that trouble is actually for resource prospecting. So this is a historic image of and something that is evoked in a lot of people's minds when you think of prospecting, in our case, resource prospecting, which is a geological science which is focused on searching for minerals and ores that could lead to finding a mineral deposit. So today, of course, it's a very sophisticated science, not any due respect to the gentleman in this image, but of course we use a lot of statistical analysis as well as ground-based and orbital exploration data, and we put all that together to try and figure out our way through new exploration landscapes so that we can look for these resources and figure out, for example, whether or not we would be able to sustain future human settlements on the surface of the moon. So Viper's deposit of interest that we are, basically collectively, our goal is to look for water ice and other potential volatiles such as hydrogen, such as ammonia, such as carbon dioxide. And as I mentioned, this is a really interesting moment because we have a lot of data that's come in, and we have a lot of folks in the lunar science community have put in decades worth of work to come up with models that help us to figure out where in the lunar South Pole would be optimal for us to go and conduct this type of exploration. So for example, in this image here on your left-hand side, you'll see the areas in blue. That is mapping data, that's temperature mapping data that shows us the areas in the lunar South Pole where temperatures basically are, they allow for the sublimation of water to not occur at that particular pressure. And so these types of tools help us to localize exactly where it is that we would like to explore. We also have team members that have put together other thermal models for the lunar surface that allow us to kind of categorize the surface of the moon so that we can make plans in terms of expanding our knowledge on where these resources might be as we traverse across the lunar surface. So this map here is actually what's called an ice stability map, and what it shows is the tiny Viper rover over there off to the corner. And then the red areas are actually where our team members have modeled that surface ice should exist on the moon, on the lunar South Pole. And then in the other areas of green and yellow, that's where the ice should probably exist within the top meter of the lunar surface. And then everywhere else in gray is where we would expect the ice to show up below that meter. So these types of tools help us to really constrain where it is that we would want to explore on the surface of the moon. Now, one thing I have to kind of express is that this is a new exploration environment for not only our team, but for the lunar science community, the planetary science and exploration community in general. When we traverse, it is one way. We actually go all the way out. I told you it's like 15 kilometers. It's a 100-day mission, and we don't come back. The mission terminates at a certain point. So you really get one shot at going across this lunar exploration terrain. So as much information as we can model, as we can put together prior to getting there, helps us to effectively be more efficient at our exploration. But nevertheless, as I will share with you, there will be surprises, and that's kind of the exciting part of actually being an exploration scientist. We do this, as I mentioned, because there is forward work that we're looking forward to, and that is the exploration with humans and robots in tandem, both going back to the lunar South Pole and then onwards to Mars. But I will tell you that for me, working right now in this moment with Viper and also with the moment that we're in with lunar exploration, I'm particularly excited about the manner in which people work. And this mission was really interesting because from the get-go, the payload that is on board of the rover was meant to be collaborative in the way that the data complemented each other. And so I will just share with you that, in fact, there were different resource prospecting payload that are on board of the Viper rover. There are 3 different spectrometers. There's a mass spectrometer, a neutron spectrometer, as well as a near-infrared spectrometer. The other thing about this rover, which is really cool, is it has a drill on it. And that drill is meant to go down about 1 meter. So I just showed you that modeling, thermal modeling map with the different ice stability regions. And I told you that we have models that show us where the ice should be on the surface, in the top meter, and then below the meter. So effectively, we're going to be prospecting with the spectrometers, and then we will be stopping in regions that we have pre-selected and that we might change a little bit once we get to the moon, depending on the data that's coming back. And then we will actually set down and drill down to about 1 meter with that auger called Trident. And so that gives us, ground-based data to back up the spectrometer data, and then it really improves and expands our knowledge. We do this because we're interested in understanding the form and the distribution and the depths to which water ice might be present in the lunar South Pole. There's other data that has come back, of course, from previous missions such as LCROSS, that shows us that we are to expect water ice in these areas, but we really want to know how far might we travel and how much in form and distribution of this type of resource could we expect. The other thing about the Viper mission is that there are 8 different imaging payload systems on board of the rover. So there are 2 cameras in the front that offer us a stereo view of the environment. There's 2 in the back called the aft cameras. And then each one of those wheel wells, you have what are called hazard cameras. I'll show you as we go along in this presentation what that all looks like as somebody who's sitting in the Mission Control Center or sitting in the Mission Science Center ingesting that data. It sounds like a lot, it is a lot of imaging, but still, as somebody who's so far removed from it, it still has to be put together so we can really understand the context that we're exploring. The other thing that I want to point out, which is very commonplace, because you would have, on our cars, on our rover mobility systems, if you will, that you would have driven to get here tonight, are lights. But that is the first of its kind on a rover, and we need those front headlights because, as I mentioned a couple of slides ago, we're heading into permanently shadowed regions. And so those areas are dark and we need to light our ways. And so that's why we have those lights on board of the rover itself. Now, again, I want to come back to the fact that these instruments are meant to be collaborative in the way that we consume the data. But the other thing, again, just to come back to the operations of this rover, is that it's teleoperated. And we can teleoperate the rover from NASA Ames, just down the street, because of the proximity between the Earth and the Moon. If you think about something like the distance between the Earth and Mars, I've just released a little speck of light from the Earth and it's headed towards Mars. That's going to take a number of minutes. It could take anywhere from 3 minutes to 20 minutes to make its way to Mars, and then it has to come back. So that's a long period of time to send a signal. Between the Earth and the Moon, however, actually I'm just going to back up. I think let's see if it's going to do this. You'll see that it's much faster. It takes about 1.5 seconds or so to actually have a signal go from the Earth to the Moon. So that's why we can actually teleoperate when we have that line of sight connectivity between the rover and the Earth, or the Bay Area here. But what is teleoperation? So to us, that affords us the ability to command the rover in near real time. And whenever I say that, a lot of people get into their minds that we are kind of joysticking the rover across the lunar surface. So it's not like that, and that's because even though it's just 1.5 seconds between the Earth and the Moon, there's all sorts of latency that comes into play once the signal actually makes its way to the Earth through our communications infrastructure and then over to the drive team who's sitting at NASA Ames commanding the rover. It's in the realm of minutes, and so we actually can't joystick. Instead, what we do is we place markers in a virtual scene, which is then translated into commands, and we place those markers about every 4 to 5 meters apart and then command the rover to traverse in those types of steps across the lunar surface. So as a scientist, when I looked at this particular operational paradigm, I was extremely excited because every time that we have to place a waypoint, every time we have to place a marker and decide where we want to go, I figured we could kind of get ourselves into that decisional process. We could be part of that with the science. And that is something which traditionally has been left a little bit to the side and then, given opportunity to come in at periods of time which were much longer than minutes or seconds. So we had to construct a completely different operational condition architecture for our science team so that they could be decisionally ready to basically take advantage of those 4 to 5 minute, in between each waypoint kind of opportunities. And that's really where I come into this whole process. So I'm afraid to disappoint, but I am actually not a lunar scientist. I'm not a flight software engineer. I'm none of those things. I actually am a limnologist, which I'll explain to you in a minute what that is. But I feel that for this particular mission, it was kind of an inevitability that I would find my way into this mission itself. And it's because it goes way, way back in my history, which I'll just share with you for a moment, that I have been wanting to be an explorer since I've been about 5 years old. Because I was a latchkey kid, I watched a lot of Jacques Cousteau. Both my parents were immigrants, and this, for anybody who comes from immigrants' families, I think you'll understand, this is really not something you want to share with your immigrant parents, that this is your life goal. But it has been. I have hung on to it my entire life, and very gratefully made a career of being an explorer, a scientist first, and an explorer, 1A, 1B, sort of like that, and paid the rent along the way. But as I mentioned, I am from Canada and made my way down to NASA Ames in about 2004 and have had the opportunity to work in a bevy of different environments, ranging from underwater settings to working on volcanoes and deserts, working from pole to pole, and all in the pursuit of understanding particular science objectives, which have been diverse depending on the area of interest that I've been exploring. But also because NASA is the only place in the world where you can do exploration in science, in engineering, in operations, in exploration, and you bring that all together into one, under one roof. And that's what I wanted to do when I got to NASA and have had the joy to do that. So I have been studying how people work, how scientists work in particular, how they work in high intensity, high tempo operations, in order to understand how we might continue to support missions, but really with science being, injected into the decisional process each and every step of the way. And then Viper presented itself, and that has been an absolute joy because the cadence of the mission has required us to actually take all that knowledge and apply it towards this particular flight mission. Now, I'll just give you a quick example of what I mean anecdotally. So this is a picture of me from many years back when I was working in the Canadian High Arctic. This is when I was doing purely limnological work, which is the study of freshwater systems. And I was trying to understand how these lakes actually changed over time as a consequence of different climatic changes in the Canadian Arctic. Now, what was interesting about this shot is that if you kind of rolled back like a Harry Potter image, probably about 15 minutes, would have actually seen that there was a bit of drama before we landed here. And that's because as we were coming down, we were supposed to land at the far end of this image. But I kind of had the hairs on my arm stood up, and I asked if we could actually do one more circumnavigation in the helicopter just to make sure the area were safe. And wouldn't you know it, a snowbank stood up and it turned out to be a polar bear. So we, in the helicopter itself was myself, a few other grad students, and then I believe a senior scientist at that time. And we all came from different disciplines, but we made the quick decision through collective conversation and consensus that we could come to the other end of this fairly large lake. I could, because I had been doing this sampling for so long, I was fairly adept at it, and I could do it fairly quickly. I could get out, I could get the work done, and we would be safe. And so we made that decision, and I'm standing here today, so you know it ended well. But it seems like a minor anecdote, but really those moments upon reflection have made me realize just how much it's important to be, responsive and adaptive and really capable of relying upon a team and having a team that you can rely on. And that makes us that much more powerful, particularly in those decisional moments when there is a lot coming at you and quick, and you only have that one-way chance to make a decision. So science optimization is something that I'm particularly interested in, and that has led me towards trying to establish real-time collaborative science decisioning systems in a number of different environments. For the Viper mission, something which has been really wonderful to be a part of is the people that I get to work with on science operations. So I am actually the lead of the science operations program for the Viper mission, but the other people that are working with me, they come from a background of field research as well. They are social scientists, they're data scientists, they're lunar scientists, but they've all had field experience, they've all had operational experience, and they know just how difficult it is under duress to actually really build consensus and how much organization has to be in place to have that happen. Now, as we've been working to create a strong, adaptable, flexible architecture for the Viper mission so we can respond to whatever comes our way in this new land of exploration, there's always been the Apollo mission as a backdrop, and we've done a lot of research into understanding science and the role of science within Apollo. And so, if you think back to the Apollo 13 movie, I think many of you have probably watched it. There's an awesome scene in it in which, the flight director, Krantz, was played by Ed Harris. He's going around the room in the Mission Control Center and asking each of the different workstations for a go, no-go, response, whether or not they feel that their systems are ready to proceed. But if you play back that little clip, whether it's going to YouTube or elsewhere, you'll notice that there's never a call out to science. There's never a call out that says science, go, no go, right? The science just isn't in the room in that decision moment. But I do want to say that it's not that science wasn't around. Science was imbued throughout the Apollo missions. The difference is that we had a science team which was separate from the mission control team. They were in a separate room, and this was a room that was filled with scientists who had been studying the moon for a long time and who were also field scientists themselves. They had helped to select the landing sites, to really understand the geology, the area, produce the maps that we're still using to this day. And they had to write a proposal and lobby for a room where they could be in during the Apollo missions, because they knew that this was the ultimate field trip and they wanted to be a part of it. And during the Apollo J missions, there was the opportunity from time to time to actually inject some knowledge back into the system in real time, and this was done rather gingerly, so very, kind of procedural and hierarchical in its nature. Now, we still find that procedure, process, and hierarchy is important in operational settings, such as what we're going to experience when we head back to the moon now with rovers as well as humans. But the difference is we have so much more to build upon. We have the Apollo missions, but now we have technology, and we have the opportunity in each one of those command steps to be much more immersed as scientists into that moment. So we didn't want to just say, we'll do what we did before. We wanted to learn about what we did, what didn't we do, and then build upon that and make it into what it could be today. And so that's the background of Apollo that I wanted to share. And of course, so much incredible data has already come back from that mission and learning, and we're excited to see what happens next. So as we built the architecture for the Viper mission, what we hung on to is that the entire mission, it isn't just about the robot. It is about the people. It's about collaboration. So what this means is that we had to build our systems for the way that people worked and for the way that we wanted them to work. So in many ways, we had to create a different culture of science where it was directly responsive to the mission cadence that was going on, in this fast-paced clip that we had planned for. Furthermore, we knew that you couldn't just have decisional input from scientists without structure. So the creation of structure has been an ongoing process, procedure, process, standard analytical methods, and this has taken time because we didn't want to just build what we thought the scientists would want. We wanted the scientists to be responsive to this process. And if any of you come from a scientific background, I think a lot of us revel in the joy of being able to learn on our own in some cases or in small teams. But then being asked, how exactly are you learning? How exactly are you accomplishing your goals? Please break that down into very minute tasks so that I can time it, so I can put it together, so I can understand friction points and conflicts with other tasking. That's a very difficult thing to pull out of a science team and a scientist. So we had to spend a lot of time doing that to make sure that that structure could be built accordingly for the team that we had. And finally, we, as I mentioned, during the Apollo era, there was no science go, no go, right? So we wanted to actually transition out of that and have science physically represented within the Mission Operations Center for the Viper mission and for everything subsequent. We're hoping that that's a foundation we can build on. So what I mean by physically represented is actually physically having scientists in the Mission Operations Center. So you will hear with the Viper mission, you will hear with subsequent missions like Viper, science, go, no go. And so that's a really exciting development for us. It sounds really small, but when you finally hear it one day, you can hopefully remember this talk and then you'll get excited. You'll know I'm excited somewhere in this world. The other thing that we had to do is to, as I mentioned, create our own culture. So we have so many different component parts to our mission in terms of the science knowledge. We have a science team that comes from different backgrounds. We have operational differences. We have instrument operators as well. But we had to bring them all together so that they all knew what to do, when to do it, and who else was doing what in every single moment, so that there was collaboration and consensus that could be rapidly built. So we knew we didn't just want a single Spock. We wanted to have the team actually weigh in every chance that we got. And that's exactly what we had to do. And one of the things that we did differently on the Viper mission, which I'm very proud of, is we embedded a social scientist into our process of building the science operations team right from the get-go. So we didn't embed her at the end, we embedded her right from the get-go, and she is actually a workplace ethnographer who specializes in aerospace workplaces. And so she actually understands and studies how people work from a social science perspective. And she was interested in helping us to create a culture whereby we're closely tied with the operations and the engineering teams so that we're all decisionally kind of collaborative. And so that was a really monumental change that we made to the way that we developed and who we developed with. And so we also use social science techniques to actually understand the history of operations at NASA as best we could and identify those missions and those research experiences that allowed us to really learn from and build upon. And also, when we put everything together, it helped us to understand where we should be innovating and where we could actually build. And so it's important not to reinvent the wheel. We didn't have much time. We started the process of building the science operations program in late 2019 and really got going in early 2020, which was also the period of time which COVID started to get going. So you can imagine trying to build something new, trying to innovate. We had to be as efficient and light on our feet as possible through that very difficult period. And social science really helped us to do the comparative analysis so that we could understand where we should innovate and where we should build. So I want to now tell you that there is, let me back up here, slides are being funky. Within the Mission Operations Center, as I mentioned, it's the primary operations center where we teleoperate the rover when it's on the surface of in the lunar South Pole. And there are sort of two rows, if you can imagine, one behind the other, of humans that are working together. And the front row is where the drive team is. And now we have physically created two roles called real-time science and the science lead roles. And they both have independent roles as well as collaborative roles to bring science to each and every command step of the drive team. And the real-time scientist and the science lead are supported by the Mission Science Center. So there is now a Mission Science Center that we've built. Again, this was built upon just years of trying to understand the science that we had to conduct, how we were supposed to do that, how we were actually supposed to make progress and make decisions quickly with the team we had. And so we created a Mission Science Center that also is responsive over that 24/7 cadence. There's a Mission Science Center lead who speaks to the science lead, and that Mission Science Center lead is basically the flight director of science and has control over all of the speed, the movement, the work that's getting done in the Mission Science Center. And they bring together the instrument scientists as well. There's a little note at the bottom of the last slide and this slide as well that you will actually hear, and it's been very exciting in many of the simulations we've ran, this MSC lead go, no go. This comes after they've called SILE go, no go. So this is a representation, a manifestation, if you will, of now the physical presence of science within these operations centers. So I'm just going to take a moment to tell you that, being here as part of an astronomy lecture, I do want to actually stop for a moment and come back to Earth and mention that so much of what we do, what we learn of course, happens here on Earth, and then we port it off into places like the Moon and Mars. But it's sometimes not that obvious in terms of why is it that we spend so much time, going out into the field here and then finding that it's actually representative of the work we would do elsewhere. But it has been something that a lot of our community does because there is a lot to learn here, basic science all the way up to this operational science. So the work that I've been doing started probably I'd say about 20 years ago. And it started actually at a lake in Canada. And many of the fundamental principles that Viper has built upon really find their roots all the way back in this project that started so long ago. And this project was actually meant to be a limnological project. So it comes back to this matter of studying freshwater systems. This lake, it's a few hours outside of British Columbia, Canada. It has within it microbialites, so they're rocks built by microbes. So I actually have a biology degree as well as a geology degree, and I was very interested in understanding, when I came to NASA, the relationship between these rocks, their environment, as well as the relationship that they might share with past microbialite developments in our Earth's history. But when I got to the lake, it was pretty apparent to me that the manner in which we were going to explore was the foundation for me to create a project that brought together operations, biology, geology, engineering, data science, all these things, which is exactly what I wanted to do 20 years ago when I started at NASA. And so with this project, because the microbialites were found fairly deep underwater, it required us to conduct some operations using diving and other tools as well that I'll share with you. So we took a look at the different scales of interest that we wanted to explore the lake at. The lake is a few kilometers in terms of its length. It's about 1 kilometer in its widest spot. And it goes down to just over 200 feet. And the microbialites are everywhere. But when we first got there, people thought they just went down to some of the diveable depths. But it turns out they're right down to the deepest depth of the lake. And so as we made these discoveries, using, first of all, some tethered robotic assets, ROVs, then we realized that, in fact, diving could only get us so far, but diving was a great way to actually explore down at the minutia level, to collect things that could only be collected by hand and to see things up close through imaging that we could take only with a diver that was perfectly still. But then, in terms of long-range exploration, that's where we brought in things like the autonomous underwater vehicle. They gave us much longer breadth of coverage, so that was an exploration tool that filled that gap. And we also had something called the deep worker submersibles. These are single-person submersibles, and we managed to get funding to train up our scientists to actually be pilots for this deep worker submersible. So what it gave us is different types of range, different speeds for exploration, different dive times, depth, access, spatial scales. But really what excited me was this real-time intellectual resolution. When we were conducting our work, we ended up setting up infrastructure so we could see the imaging come back in real time. And it was very exciting to see how the work system responded, depending on whether or not we were moving quickly or slowly, being able to collect at centimeter scale or on a more broad scale. And that led us to create an understanding and with our community that, in fact, this type of work, this kind of holistic field work and conducting research with all these component parts integrated was actually a wonderful analog to space exploration itself and the manner in which we would be exploring the Moon, Mars, and elsewhere. So working at this lake, this very, seemingly innocuous lake in Canada, we did a lot of kind of foundational building work. We actually tethered our deep worker submersible to a surface operations boat, and allowed ourselves to transmit all of the data that we were accruing, the positioning, the voice data, which is the observations coming from the scientists, the video, back to a mission control center that we set up on shore and that we filled with scientists who had roles that they were to develop and mechanisms for working protocols and so forth. And we actually injected communication latency. So we mimicked what it was like to transmit between the Earth and Mars, and the Earth and various stops along the way to Mars. And so we played with that, conducted research to see how our work system would respond. And from that, that created for us a whole bunch of questions, a whole bunch of needs. We started to really see that if the team could not all gain a shared awareness of the exploration context, if each person was seeing something different, that created so much friction in the environment. I think, many of you have probably had similar day-to-day experiences where you're in the same place at the same time, but you're seeing something different from your partner. And it's so frustrating because you're like looking at the same thing, but you're not having the same conversation. So that's even more so when you're limited in terms of exploration and you're seeing the world through those tiny portals, those tiny lenses of imaging. So our goal was to create a data system that enabled shared operational and scientific awareness, one that sparked collaboration, that enabled curiosity, one that helped us to be, decisioning and influential under real-time or rapid accrual of knowledge kind of timescales. And we also knew that we had to have a system that helped us to keep time and to replan very quickly when the unknown presented the unknown. And so this was the start of where we started to put together these things called exploration ground data systems. And this is really where we started to lay the foundation for democratizing the access that we had to, all of our team members had to data that was coming in from these extreme environments. And this led us to do some research on shore in terms of gathering data as it came in, analyzing it as it came in, and then putting that back into the system. So this is some imaging from 2009 where we had the deep worker submersibles as well as divers taking images, sending it back in real time, and our scientists were categorizing the microbialite shapes and forms based on historic morphological classification schematics, and then creating maps as quickly as they could to help us optimize the science return while time was ticking. Like, this is something I want to emphasize. We didn't have all day. The deep workers could only last up to about 6 hours underwater. The divers were diving at depth, so they had a very limited amount of time underwater. So this was really the first kind of experimental work that we did to try and understand how to create that structure, create that consensus building structure to help us be decisional when there were literally scientists whose lives were on the line. From there, the research went through several different phases, went through several different environments, and then we also had this project that took us to a couple of different volcanic sites, and we formed a program that was really kind of the next evolution of the Pavilion Lake Research Project, which I just shared with you, and that was called the Basalt Program. With this program, we moved to 2 sites, one in Hawaii and one in Idaho, that were meant to be Mars analogs. So basically, they were geologically and potentially biologically interesting to our team from an analogous standpoint to our destination of interest, which was Mars. But bigger than that, we wanted to use the experience of the field work there to create an environment that was akin to Mars exploration with a remote science team remaining on Earth. And we wanted to particularly explore the question of whether or not across Earth and Mars communication latency, so that delay that I showed you in the animation earlier, whether or not, I'm just going to kind of paraphrase all the wording, that's the proposal speak, but whether or not a science team here on Earth could be influential to an EVA, an extravehicular activity, an exploration activity happening on Mars. And despite these latencies, despite the communication latencies, the prevailing thought in the moment was no. You would basically have to relinquish any sort of expectation of control of decisional input because of those latencies. It's too hard to do when a team is out on EVA. They cannot stand still. Their life support, their health and safety is number one. You would really want to dislocate science decisioning from that process, from the Earth, and just allow it to take place entirely with those astronauts on Mars. So we wanted to explore that because we didn't, that was the prevailing thought, but we wanted to really explore it from a research standpoint. So we looked at kind of the foundational architecture at the time, which was the design reference mission that was published from NASA. And from there, we designed a program that had 2 scientists out on EVA, representing, in one case, operations, the other science. And they would go out and we would spend we spent probably 93, 94% of our project, which lasted 4 years, planning, preparing, running engineering runs, all sorts of things before we even got out to the field. So you can imagine, like, once we got there, there's a ton of preparation and that structure already in place. And then what we did, as I mentioned, is we had the 2 people out in the field conducting the geological and the biological research. And then we had a team of scientists that were 15 to 20 kilometers away from them, but more so, they were kind of dislocated from the temporal space that the astronauts were in. So we had Mars time represented by those that were out in the volcanic site, and Earth time represented by those that were back on in the Mission Science Center. And we also had what's called an intervehicular workstation, which was also on Mars time. And those people are basically the flight directors sitting in maybe a mobile command center on Mars that were helping the communication really kind of flow through smoothly. And they were helping to facilitate the communication between the Earth and Mars. So it's an entirely different talk for me to tell you everything that we did, but the basalt, if you just kind of Google basalt, NASA, and research and astrobiology, there's a lot of things I can tell you again later. But basalt and astrobiology, there's a special issue which is, you can all access, it's free and open to everyone, and you'll see many of the papers that came out of it. One of them talks about the architecture that we built to examine that question about whether or not science could be influential while the EVA was progressing. And we put together an EVA, a structure that allowed us to have the astronauts walk in these circular patterns and explore areas of interest such that by the time they never stopped moving, and they always started with taking imaging, and then they kind of got sharper and sharper with their refinement. So the intellectual resolution was increasing with each pattern. And as they came back to the start, all of that information was being transmitted to the scientists sitting on Earth. And as soon as that data was received, each scientist was given their structure, their procedures, their analytical methods, and they were meant to rapidly triage and basically rank order their samples that they were interested in gathering. And then that was constantly transmitted back to Mars. We did this constant transmission, and we did this in a very timed, deliberate manner, because we knew that there's always the possibility that communications could get stopped, could get shut off. So we wanted to see if we could constantly stream information back that would give the astronauts or give those on land, on Earth, as much knowledge as possible to make the next good decision and the next good decision. So it's called the circuit sampling architecture, and we tried this many different ways, many different times, and it was extremely influential in helping us to understand that, in fact, you can be decisional, you can be influential despite those latencies. And that helped us to really understand the value of that kind of structure going forward, even if we're dealing with timescales like 1.3 seconds when we're on the moon. From the basalt volcanoes, we went to sea. So our team, some of us from basalt actually transitioned over to an oceanographic research program. And what we did here is we, again, had a natural sciences, a social science, and a technology development component. And those all came together, were integrated, because we really wanted to understand how the oceanographic community here on Earth teleoperates, how they bring their scientists onshore into their exploration at sea. When they're at sea, there are limited bunk beds on the ship. So we went to sea on the Nautilus. We sailed in 2 different locations, one at Gorda Ridge and one just off the coast, again, of the Big Island of Hawaii. And we were conducting work, again, that was, had a component of geology and biology and had a space sciences application. But my interest was, of course, in understanding the work practices of this new community and how we might learn from that to support future planetary work. And so they have very interesting work practices. We actually built upon what they did in terms of their mission control centers, and we actually started to build systems that allowed us to have periods of sort of that disconnect where you have to transmit and as clearly as possible in a very structured way, then actually wait for that to come back and then make those decisions and continue that effort 24/7. So in this particular project, I'll just share with you that, again, many different learnings, but we built in we put a lot of effort into the data systems in this case, which had a direct influence on what we built for Viper. And again, one of the issues for us was this need to create a shared awareness of the environment that we were exploring. So when you explore underwater, when you explore in space, you get a very limited view of what it is that you are exploring. And everybody can see something different in that. Of course, like there's limitations because you all see the same data, but it's remarkable when you have to bring everything together, what kind of frictions can arise. So the data system, the ground data system and the exploration tool that was built, I think the video is going to start shortly. There you go. Allowed our scientists as a collective, both co-located as well as remotely, to get in and to manipulate pre-existing maps of the area, and then to actually pinpoint exactly where it was that they would like to go, and they would turn different map layers on and off so that they could get a different perspective on what it was that they were looking at depending on their interests. But the important point here is that anybody could do this. This wasn't limited. This is a web-based application that was developed and evolved through all these different projects. So any of our scientists sitting anywhere could gain access to this and could look at the same thing at the same time. So we created this shared awareness, which was important because otherwise there were a lot of friction points in the system if people they didn't see the same data at the same time. And so these are some testimonials that came in from our scientists. They were all oceanographic scientists. They had never worked with this before, and we're so excited to just have the opportunity to get this experience, to quickly access these map layers, and to work with them as a collective. We also tried to promote collaboration throughout the mission itself, both in the planning before we got to sea and then when we were at sea. And so being able to turn on and off all these different layers and then actually plan where we wanted to sample and when and why, all the different timings that were put into this took a lot of effort. And again, this was teasing out from the scientists how they were going to work, what component parts were they needing to actually activate and how long that would take. That's called the operationalization of science, and that's what we had to work on. Another element that has since been evolved to support the Viper flight mission, and which has really become important, is this ability to look at the same thing at the same time and to show what it is that you are finding important. So this ability to annotate, and their ability to annotate and to share it amongst everybody, because something that we find is in these linear kind of mission control centers, sometimes you can't see what's happening a few workstations down just simply by the construct of the way that the screens are set up. There's a whole other conversation there regarding whether or not you should be in a linear row or maybe you should be in something more circular, of course. But just being able to look at a screen and see what somebody else is doing and have that update in real time, this has been incredibly powerful for exploration science. The matter of time. Time is everything. It is everything here on Earth. If you're raising a teenager, you probably totally know what I mean. But it is everything when you're dealing with high-intensity operations, when you're dealing with moments like I showed you where you have 4 or 5 minutes at most, which means within that you have seconds to get any decisions to be activated to when you have a system that's only going in one direction and you can't come back and have any do-overs. So I hope I've stressed you out just a little bit. But in this case here, we're allowing the scientists to actually look through what has happened in the past, actually look at events and flag moments in time in the past because they might influence what's happening in the future. this has been very important for us in terms of time management and looking at the past to understand the future. The other thing I want to note is that we would generate, so much opportunity within the data system that we created, but we also knew that there's only so much you can plan for when you're exploring. And then, of course, as I mentioned, you know that the unknown will deliver the unknown. And so we actually had to plan for the fact that we needed the data to come out of the system so that our scientists could work in their mechanisms with their specialized software to give us, specialized information as the moment demanded it. So these systems were designed not to do everything, but rather to support exploration. So it's a very particular perspective, and that we never intended to build only, to do everything within these data systems. But again, just coming back to the fact that we tried to create a shared awareness, we've brought that perspective, we brought that research into Viper, and we've been sharing it broadly throughout the agency as well, that this is important, especially when you're conducting lunar science or anything at a high tempo. So I'll just show you some imaging as it evolves through, I started you on the moon, I took you to the Earth, I'm going to come back to the moon. So this is some orbital imaging that we use to plan as we get further and further into our planning stages. And we're, looking at it from top down. Those circles that you see are the different science stations that we wanted to explore. They represent different ice stability regions, so deep, shallow, deep, dry, as I spoke to you about earlier. And the little rover is that blue dot with the arrow. So we're getting closer and closer with these imaging and coming in. When we actually get to the surface of the moon, this is simulated data that you're looking at. We run these simulations using a simulated lunar environment. We have, as I mentioned, going back, about 40 minutes ago, 8 different imaging systems. You would think that's a lot. This is what we get. This is what it looks like through some of the data systems that we are using to visualize data and share access to that data. So when we look at this, it's exciting, it's influential, but we know from past research that we have to put it together in a way which is more contextual based, so that scientists can really understand everything that they're looking at in a more holistic manner. So as we go from a top-down view to actually reacting to the environment that we're in, we've created a rapid stitching tool that allows us to take imaging coming from our cameras, our stereo cameras in particular, and put them together into panoramas. And on the side there, as you see the panorama kind of flipping by in this video, you see there's 2 little kind of markers that allow us to understand the directionality of where we're looking along the lunar landscape. So we don't give this just to the flight director, just to the drive team. We give this to everybody. And so again, it's that perspective that has come from the Earth, come from these projects, underwater, in all these different weird places, that we know that it's a theme that is useful. It doesn't matter to what scientists, where they're working here on Earth, and certainly when it comes to the moon. We also know that scale is something that we struggled with underwater. Directionality and scale is very difficult, and it also is a struggle on the moon. And so our team has been working on what are called disparity maps, which allow us to understand within the lunar landscape what exactly it is that we're looking at from a scale perspective, so we can take a look at how far, what's the distance to a target. We can understand what the distance is between 2 particular targets. And so this is all development work, which again, we pushed for because we know that for science and broadly operationally, this is very useful to have. All of this work, no matter the fate of the Viper mission, it is learning that is now within the collective. It is learning that is within the agency and that we're sharing. I'm here talking with you all about it. And I will tell you, it was a bit of a journey to be able to get here, and Andrew knows it too, to be able to share this with you, because we are in a period of transition. But it is exciting because we know this can be built upon. Have we solved everything in terms of how to do this kind of high-intensity decisional operations? No, but we got the chance to do it this particular time. We're hoping that it manifests accordingly into the Viper mission being flown. But no matter what, there will be opportunity to see it in action. We also know, as I mentioned to you, that this work hasn't been singularly focused on the lunar landscape. It's ebbed and flowed. It's applied, it started with research here on Earth. It's been applied through to different architectures dealing with Mars exploration, and then brought back into the lunar exploration scape. I also want to share with you that the installation of science, of the operationalization of science and the installation of that into a collaborative format when it comes to Earth-based operations, particularly in the realm of, let's say, emergency operations, any sort of reactive environment, that is something that we're really excited about as well, and having conversations, because there's all sorts of opportunity there for scientists to be adaptive and flexible and installed into the decisional complex of all of these different settings. I just want to leave you that this point that I brought up earlier, that it's not just about the robot, it's about the people and it's about collaboration, and we try to design our systems with that in mind. And this is the case whether or not we're talking about humans here or humans off planet. And for me, the exciting part is when we have humans in 2 different locations, and that collaboration has to be enabled too. So that's what I'm looking forward to in the future. Maybe I'll be able to come back when there's a 35-year-old talk or some period or something. But thank you very much for staying here with me tonight, and just thank you.
Thank you very much for such a wonderful presentation. So, as far as I understood, you developed such a framework that you can make real-time decisions for the science to go or no go. So, do you think your development, your framework could be used in the NSF to make decisions on the grants, like real-time? So, for example, like somebody submits a grant, and there is a deadline, and then there is a waiting time, and like, so it's a real time,
Okay, I love this question. This is like the best question. If anybody like just labored over the decisional period for a research grant before, like raise your hand, like it's awful, right? So jokes aside, I mean, I see all sorts of possibilities for this. There is broad scale application. We have what I didn't get into is the fundamental process of how we develop the process. And there's an architecture underlying the architecture. And I honestly think that like so many things that couldn't have an improvement in terms of efficiency, and in those realms there, like grants are reviewed and then decided upon through consensus, right? That's the ideal state. And so that's literally what we have built is a architecture for building rapid consensus. If you know somebody that's interested that would like to talk, I mean, we are open. We'd love to, my favorite planet is the one we're on right now. And so I hope I can make it, as efficient as possible and make scientists' lives a little better here and there whenever we can. But thank you. That was like very unexpected and creative question. Thank you. I feel your pain, man.
Thank you for a fascinating talk. We have 25 years of experience by science team and engineering teams operating rovers on Mars. And you never mentioned that, whether it's relevant. Of course, it's very slow motion compared to what you're doing, but it seems surely has to deal with similar challenges.
Yes, absolutely. And sorry, I didn't mention it, but I put a picture up of, I think I put Curiosity up. It's completely relevant, absolutely. Now, some of the analytical work that we did early on with our social scientists really, kind of spearheading a lot of that research is to understand the timescales of decision making. And so we wanted to line up, like there are periods of time where any of the science teams are in deep, right? It's very intense, and there are just like seconds to minutes that they have to really dig in. But in terms of when command cycles occur relative to when actually those decisional periods are and those consensus building periods are different than what we experience with the drive team teleoperating the rover on the surface of the moon. So yeah, and sorry if I wasn't clear about that. Absolutely, like we looked at so many different Mars exploration missions and looked at that cadence. We also looked at the visualization. Some of the panorama work that we are doing here is actually built upon the Mars missions. So one of the things we hate doing is reinventing a wheel, but one of the things that we need to also understand is when a wheel actually should be invented, because there are moments for that as well. So definitely, that was very important to our research. Thank you.
Could you explain what you will be doing while the rover is in the dark period?
Yes.
Both here on Earth and on the moon?
Yeah, absolutely. So the rover itself goes into a hibernation mode. And in that modality, it is literally cut off. And so there are certain, the payload has to be placed in certain modes and so forth to survive that period of time. The rover is built to survive the hibernation periods. What we're doing here on Earth is, so that's a different modality of operations that we'll head into. So we had planned to move out of the 24/7 operations mode and move more into like a work, kind of regular work hours mode. But the team that would have been co-located here at Ames, many people would probably go home to their families in that moment in time, but still be analyzing data, and we would have set requirements for each of the scientists. They would be tasked with particular analytics to be put back into traverse planning. And all of the traverses coming up for the next lunar day would have to be reevaluated based on the learning. So one of the important cycles that happens both on a second-minute tactical kind of level to more of these strategic level moments is that anything that we accrue in terms of knowledge should be put back into the system, and that's basically what we're working towards. And that safe haven mode presents just a little bit of a different time scale of work. But it was amazing once we started to break down the days into hours, into minutes. I think basically people would be going home to say, hello, let me take a nap, and then I have to get back to work. So there's certainly, as we started to really examine things down at the minutia, literally, it started to become apparent that that safe haven work period was, as intense as the period that we had connectivity. Thank you for the question.
Hi, thanks for this kind of interesting peek behind the veil here. I'm just curious because I kind of lack the imagination. Can you give us an example where this Mission Science Center lead would say no-go about something and what the consequence was and the actions would be after that?
I love it. Yes, thank you for the question. So one of the possibilities is that our data systems aren't working in the Mission Science Center. So as I mentioned to you, this shared experience, this shared access to all of the data, to the visualization of the data, if something failed in that and we didn't actually get telemetry at one of the workstations for the instrument scientists, or we weren't actually seeing imaging, then that would mean that doesn't check a box. So we're in a no-go moment there. But any of those situations in the Mission Science Center would be then compared to what's going on contextually with the entire mission. And so science is operating, and it's there to enhance every decision. It's also there to make decisions about where to drill, for example. But if everybody else is ready to go, like time is ticking. I showed you that, the ebb and flow of the shadows, right? We cannot fall behind. So being ahead or behind is always important for us to be. In fact, I'm totally not even using the right words. It is like of paramount importance for us to be reactive to. And if the rest of the operational system is ready to roll, and we have a circumstance where some workstations are not fully operational, but we could get them operational, that's the kind of thing we would work in real time, and you can imagine it would be pretty intense. And so that may have the consequence of the flight director saying, no go. I would guess that it would still be, if everybody else was ready to go, it would be a go, and then we would solve the issues in the Mission Science Center as we went. And one of the interesting circumstances that leads me to kind of imagine it going in that particular way is because we have that physical science representation up in the drive team, and we also have them connected to the Mission Science Center through that kind of the hierarchical connection and the structure in the room. So even if we couldn't see data, but they could see data somehow and their systems were a go, I think there would be a way to communicate to allow us to proceed until our systems got back online. we didn't simulate into anomalies, which is what you're describing here. And so our simulation, like hours, ran in, through a whole bunch of different scenarios, but we didn't actually hit that kind of anomaly testing before we hit that interesting period last summer. So that would certainly, resonate with what our testing would look like when we got into anomaly testing. Thank you.
Thank you.
All right, so 2 more questions.
Thank you. Okay, sounds good.
Yeah, I like how you organized your presentation here for that. So you describe how over the years, through your past experiences and others, how they assemble the mission, the collaboration, the organization, et cetera. And then I'm thinking, okay, let's say a Viper landed on the moon 20 years ago, that it seemed like the mission profile would be completely different, even though the technology is better, but so how, and then I'm kind of thinking, well, what is going to be like 20 years from now? Like, how would such a mission be organized? Thank you.
Yeah, great question. I mean, I think it's hopefully better and better. I think if you had asked Darlene 20 years ago, I would have been like, let's go, like, I'll figure it out, but I have more knowledge now, and we have people with more knowledge now, and then I'm assuming that will continue, that continuum as you described it will be the case, absolutely.
Hi, thanks for this fascinating talk. Great visual too, by the way. Hope you warm up pretty soon after we're done here.
So cool.
Let's see, you being a limnologist, which I believe is like the study of lakes and sedimentary stratification and so on. So I guess you would be getting into, you were talking about the microbialites, which I guess it's basically rocks built up by living matter. And are they related to stromatolites? I mean, is it the same thing or different class? Or?
Actually, it's a broader term. So stromatolites fall under the category of microbialites. There are thrombolites as well. It just depends on the internal structure of the rock itself. So a stromatolite has layers to it, which you've probably, like, it kind of looks like, it's the classic, microbialite. This is like a whole other geek out session, right? And then the thrombolites have more of a clotted interior to them. So at Pavilion Lake, at a kind of millimeter to centimeter scale, we actually did see some strombolitic deposition. But then if you looked at the broader structure itself, like the ones with the chimneys coming out, and we actually took samples of what it looked like in the interior, those were all clotted. And so it was really interesting. You had these different structures building up at different scales, which again were only noticeable because we were sampling at different scales and observing at different scales. Yeah.
Yeah, cool, thanks.
Thank you. Thank you.
Thank you very much.
Oh, thank you.
Thank you, Dr. Lim. I think everyone joins me in hoping that this stuff gets applied in real time to real missions. But thank you so much for sharing all this with us. Thank you all for coming.